So this is week 4 of the course, Transport Phenomena for Non-Newtonian Fluids. And so far in this course, we have started with the basics of Newtonian fluid, and then how this basic concepts related to Newtonian fluid and basic definition related to Newtonian fluid can be translated to define the non-Newtonian fluid, and then the non-Newtonian fluid, which is most of the general real-life fluids are non-Newtonian. We wanted to study a rheological property of them in very step-by-step manner. So in the second week, we have learned about how this capillary viscometers work and how reliable these capillary viscometers are for computing the rheological properties of or experimentally evaluating the rheological properties of any unknown fluid which is non-Newtonian in nature. So whether a fluid is non-Newtonian, it will be only known once you are going through these experimental activities. Like the second week was around this viscoelastic capillary viscometer, and another next week after that was on rotational viscometers or rheometers, where these different types of rotational rheometers we have studied. First was this one cylinder is rotating inside another cylinder, so concentric cylinder, in which the central cylinder is rotating with a given RPM or the rotational velocity. And then the next one was around this the cone and plate kind of rotational rheometer setup, where this cone rotates, and why the cone has been taken as a geometrical feature in order to evaluate the accurate rheological measurement of the unknown fluid has been explained. And then the next we have discussed about plate type rheometers, where the one circular plate is rotating against the another circular plate, and how it is advantageous in some cases and in some kind of fluids, where the main criteria was using this rotational rheometer you was able to compute this normal stresses. So in the non-Newtonian fluid we have seen that these normal stresses. So let me just, I think I am still audible, so let me just present my screen so that things become clear to you. So this rotational rheometer we have discussed. So let me just put it here, my screen for week 4. Let me just close week 3 and it's week 4. So this transport phenomena of non-Newtonian fluid, it's live session for the week 4, where basics of basic transport phenomena, where you are in this particular 3 lectures. In 4th week we have gone through basic derivations related to continuity equation, basic derivation related to Navier-Stokes equation, and so far we have always derived the Navier-Stokes equation in terms of Newtonian fluids. Like there are some assumptions after which you have the final expression, the very classical final expression that is most of the time used in the Cartesian setup are for the Newtonian fluid. But in reality, where to stop during the derivation, so that the equations that you are getting is more generic and can be equally applicable to the non-Newtonian fluids, have been also discussed, right? So, and then you came to this this non-isothermal. So these were this equation of states, right? So then non-isothermal for thermal energy balance equation has been derived, and there was this balances for all the energies, for example the kinetic energy, potential energy, and then this internal energy has been derived, and later we have solely derived the balances for the internal energy, enthalpy, and then it has been changed to the measurable quantity. So measurable quantities like temperature. So the equations, whatever thermal balance equations we were deriving, they were having some property like internal energy. They are intrinsic, implicit in nature, but uh, in order to have clear understanding and experimentally validate those equation, you want something which is measurable. I mean, like temperature, pressure, velocity, these kind of things. So the equation, any balance equation that you are deriving, if it is in the form of measurable quantities, then it actually becomes easy to implement them in the real life, rather to have them in terms of some implicit thermodynamic variable, for example enthalpy or the entropy, so to say, right? So with this line we will be solving some question in this particular lecture. So these are some questions that we will be solving along the course of this particular 2 hour, and then these questions will be definitely helping you in solving your weekly assignments, as well as some of the questions you may think of that you will be getting them in your final examination. But at the same time I will be giving you a revision session for whatever has been taught in the entire week, using the same slide that sir has took, because the slides are very clear and crispy, and it's good to revisit them before solving the questions that are around them, right? And what is the main purpose of this particular class is you have revision of whatever has been taught in the entire 3 classes of the week. Another one is, once you are capable of feeling the equations, so I will be generating a kind of feeling with each equations. It's not like just mathematical juggleries or complicated equations here and there, and then you are actually missing them out because of the complexities associated with them. Rather, I will be simplifying them, giving you some analogies and corollaries with the real life, where you will be actually facing these terms. So each terms, what the physically they mean, and how these terms are actually dictating the rheological property of fluid, and how these equations, these governing equation that was the part of 4th week, are actually helping us to understand, or the better understand the framework of the transport phenomena related to non-Newtonian fluid, and how we will be implementing these equations in subsequent lectures which will be coming along the time in subsequent weeks, right? So let me just open the main lectures that is here. Let me just, so these are assignments, and I will be opening week 4. So week 4, these lecture number 11, lecture number 12, and lecture number 13, these 3 lectures were the part of that. So I will be very complicated equations are there, so I will be sometimes looking at them so as to make it easy for you to understand. At the same time, I will be actually dictating the conceptual understanding around them, so that things become easy for you in the long run, right? So let us just add a slide here, because these slides will be anyway helping us. Yes, and set my pen if it is working. So yes, it is working, right? So what I wanted to say, that I think you can see the main screen, but you cannot see the screen which is having the actual derivation. So I am looking at the slides meanwhile teaching you. So this course, any equations that you fear about can be revisited. So many standard books, whatever standard books has told you about, like Bird, Stewart, Lightfoot, or then this Dean's book, and then Fenton's book, Chabra, R.P. Chabra's book, and then this Moxco books. So these books are around rheology and the transport phenomena. They can be equally referred along with the course of looking at the or learning the course. right? So so that is the main agenda of the course. So let me just point out some of the lectures. So what I am saying is I will start with the first lecture where sir has derived this. So till now you understood that this this transport phenomena, right? This transport phenomena is linked with each of the possible transport that can happen. It's transport of momentum, right? Transport of momentum, right? Which comes under the umbrella of fluid mechanics, right? And then this transport of energy, that was the third lecture of the week, and this transport of momentum was the second lecture of the week. Of momentum, then its energy, its heat transfer, right? And then this transport of chemical species, which comes under the umbrella of mass transfer, right? Transport of chemical species, right? So it comes under the umbrella of mass transfer. So what I'm saying is, in order to grasp this particular subject, which is the transport phenomena, you need to have a fair idea about these subjects, which is fluid mechanics, heat transfer, and mass transfer prior. Or even if you are not having, the fourth week was about that only, so that you can have at least some preliminary basics so that you can brush up those concepts and then jump into the main agenda of the course, right? So so why these are important? So what I'm saying is design and control of operations, right? Let me just see if things are okay with the online. So you are presenting to avoid infinite mirror. So my screen anyway. So no problem. These are, let's fit it here. Okay. So all these lectures will be recorded and you can revisit these lectures as per your pace. Okay, and then you can, so let me just fix it if it can be fixed into the screen. Yes, it is right there. Let me just fix it if it is fixing. Okay, so okay, so now it is okay, clear to you, right? So design and control of operating conditions of many unit operations and unit processes require knowledge of transport phenomena, right? So any processes or the unit operations or unit processes such as flow through the pipe, flow and heat transfer from cylindrical and spherical cylinder and sphere to the fluids, diffusion of species from falling film, evaporation of the column of the liquid and boundary layer flows past flat plate. So boundary layer flow past flat plate. So these, I mean these, any boundary layer, suppose this is flow of a flat plate. Okay, so these these are associated with the heat and the mass transfer to the surrounding fluid. So associated with heat transfer, mass transfer, and momentum transfer. No, sorry, fluid mechanism. The surrounding fluid. So a prior information on performance of industrial performance is industrially important setting can be achieved if you are actually looking at these aspects carefully prior to the to working with any unit operation or unit process, right? So why these transport phenomena should be studied together? So why, as sir has stressed it many times, if you remember, this has to be studied along with like all. You cannot solely learn heat transfer, mass transfer, and fluid mechanics separately. Rather, these phenomena are happening simultaneously in real systems, right? So governing equations are closely related in these terms. If you are thorough with the fluid dynamic equations, then it is very easy for you to connect with the kind of equations that you will be getting for the transport of heat or the transport of species or the chemical species, right? So mathematical solution approaches are similar, and so the molecular mechanism are very closely related. So it is very easy for you to study them together, and that's why this subject comes into the picture, right? So let me just see what is there. No issues, right? Now what I'm saying is I will be just having you revision, because out of these these lecture, this particular week, mostly the transport equations were derived, and these equations are lengthy. So I will be revising you, and at the same time I will be telling you all the explaining all the derivation steps and the equations very clearly, so that you get to relate to them, right? And then because framing question out of this at this stage is not easy, and rather if I throw some questions over here, then it becomes much easy if the questions will be thrown based on the setups or the systems that we will be dealing in the subsequent lecture, right? So getting insight into the equations, getting insight with the framework or the kind of assumptions that has been taken for a particular governing equation or deriving the particular governing equation is the prior most important thing that has to be noted at this stage, right? So I will be again explaining the kind of phenomena that was there, okay, and then we will be discussing it very carefully, so that things become very easy for you, right? So let me just have my piece. Okay. So let me just put my. So sir has told you an example about the stir tank reactors, right? So let me just draw, or rather if I draw it, or yeah, let me just draw it, right? So this was the stir tank reactor, and there was this mixture, okay? So you had your feed in Fi Ca0 Ti, right? And then there is this out FF Cc, and then yes, product out, right? And then there is extreme which is getting recycled, right? This recycled stream goes to here, and the volume of the fluid you are having till here, right? So the concentration in here is Cb0, and the reaction that is taking place in this vessel is A plus B. These two reactants are reacting to give C, right? So that's why this C was here, and then reactant A was there, and B was initially inside this vessel, right? So through this, sir has explained you about three things. One was this, uh, what we say, microscopic level study that is done. Another one is, this. One was the microscopic level study. Another one was this macroscopic study. Another one was molecular study, right? So this fluid mechanics, which is the continuum, where this Newton number, which is this mean free path divided by characteristic length, is a bit, is low. Is coming under the Newton number low condition, where this this values which are for the Newton number are in lower range, where this continuum hypothesis is valid, right? So this continuum hypothesis, keeping in mind, we will be discussing how different levels of uh, this analysis that are there are discussed here, right? So consider a continuous stir tank reactor in which reactant A is converted into product C, right? As shown in the figure that we have drawn, right? The reactant and the products are dissolved in the liquid phase. The reaction undergo so this, if you see here, both are happening together. So mass transfer, heat transfer, and momentum transfers are happening together, right? And if they are happening together, then it is very important for you to actually understand how and why these are interrelated with each other, because then only you will be actually having thorough understanding about the phenomena that is there, right? So the main thing that I wanted to say is this this reactant which is feed in A, they are getting intermingled or mixed together with the B, and the reaction goes on because enough surface area of the B is exposed to the A, and they are having intermingled contact with each other, leading to the enough activation energy so that they convert themselves to the C, right? So this, either it is exo or endo, for the time being we are not bothering about that, just this activation energy is the important thing. Okay, so reaction coordinate to activation energy, right? So here whatever is there at the local level, at this zone, at this zone, at this zone, so there will be a property which will be the average property of entire fluid content inside this vessel. So that is the macroscopic level of the consideration, right? And if you consider a control volume of suppose 10 micrometer by 10 micrometer, and in that you are analyzing the system like we usually do in the continuum hypothesis, that is microscopic analysis. And if at the molecular level you are looking at how the molecule of A is interacting with the molecule of B, so there will be different density, different viscosity, and different surface tension or other rheological property at different zones or different points in this particular beaker or the stir tank reactor. Then this becomes important for you to actually have clear molecular picture so that you can predict the exact rheological property of the fluid which is coming out of the reactor as a product, right? So now afterwards you had this microscopic, and molecular level of understanding. So I will be just telling you very briefly things, and then we will be moving subsequent ahead, right? Macroscopic level of balances, and then there is this microscopic level of balances, and then there is this what, molecular level of balances, right? Molecular level of balances. So we will be solving some questions around this also. So let me just start with the molecular level because that is more fundamental, right? So fundamental understanding in terms of molecular structure and internal interaction forces. So molecular structure and interaction forces. So you may have some questions or the objective type question around this. Which of the following level of rheological measurement of the transport phenomena study involves molecular structure and interaction forces, right? Then you need to have clear idea about this, which option you are going to choose. It is molecular level of description, right? Theoretical physicists or physical chemists are interested in this detail. So all the MT simulation or the molecular docking, whatever is being done, or this DFT, density functional theory. So molecular docking, DFT, density functional theory, okay, density functional theory, right, are coming in the umbrella of this particular thing, right? And here these details are essential for processing involving complex molecule, extreme range of temperature or pressure, or chemically reacting species. So these are very important for the chemically reacting species. Important for chemical reaction. High temperature, high pressure, complex molecule, right? Okay, you got it. And here the length scale is what? Length scale is 1 to 100 nanometer, 1000 nanometer. It's 1 to 1 micron, right? 1 to 1 micron, right? So conservation law plays a key role at all levels of transport phenomena. So whether you are at the molecular level, macroscopic level, or the macroscopic level, these conservation laws will be there. But the way these conservation laws should be implemented to the system differ, and that's why these level of analyses are separately studied in different subjects, right? And then another one is microscopic level. So it is interior detail of the system is assessed, what is happening to the fluid mixture in small region within the system, right? So length scales are order of micron to centimeter, right? Here length scale are 1 micrometer to 1 centimeter size. And here the develop equations of change for mass, momentum, and the energy within the small region. So that is small control volume that we used to take in any classical fluid mechanics heat transfer or mass transfer system. That is the one that comes into the microscopic level, and this is the place where the value of Newton number is actually coming in the zone of it's like a lower value, right? So let me just tell you about the Newton number in detail because this is the important concept and it will be actually many times you will be using it. Okay, so it's like new slide here. So it's like Newton number is a dimensionless number defined as the ratio of the what? Mean free path. So Newton number, it's like equals to mean free path, mean free path divided by characteristic physical length scale. Okay, representative physical length scale, physical length scale, right? So mean free path to the physical length scale, right? Let me just see where is this. Marker is not coming up. Let me just fix the marker, right? Right, is not coming. So we see it. So yes, it is okay from here. So physical length scale, right? And this is lambda by what? L. This is the characteristic length scale. Okay. So molecular mean free path lambda is the average distance between the molecular travel between the collision, right? And then physical length scale often represent a characteristic length scale, such as the radius of the object or fluid or gap length between where the transport is occurring, right? So what I am saying is, if you see, there are this. Suppose this is the system, right? And from here the fluid is flowing. So here continuous flow is here. So here Newton number is say 0.01. So low vacuum, right? C Julian, right? And then if this around this length scale only, so this is the length scale and this length scale only. If this fluid is moving, but this fluid is having some interaction with the surrounding. Here there is some interaction, here there is some interaction, right? So for this case, you will be having Newton number between 0.01 here 0.5, right? Still it is same. Here medium, very low vacuum, it was medium vacuum. And then there is this ultra high vacuums you will be having when Newton number is very high. So here there will be lots of interaction. Okay, this was this L. And your Kn will be greater than 0.5 ultra high. So the thing is, what I am saying is, so this the value of Newton number is actually telling you about many facets of fluid flow, right? So what it is saying is, if Newton number is less than 0.01, around this also you can have some questions. Continuum fluid, right? Flow. Classical fluid mechanics applies. Here the classical fluid mechanics applies. Fluid mechanics applies, right? Okay. And if this value of Newton number is here, which is very much possible in the systems, here you will be having stream flow result. Stream flow result. So there will be some velocity flip at the boundary side. And then if your let's say number is here in this range there is transitional flow. Transitional flow. And if there is this Knudsen number greater than 10, free molecular flow, molecules move independently. So it's free molecular flow. Okay. So it is widely used in the microfluidic MEMS design and the porous media transport and rarefied gas dynamics. High Knudsen number indicates rarefied gas where the continuum assumption breaks down, and mathematically for gases the Knudsen number can also be related to pressure temperature, molecular diameter and gas properties. Its use helps to decide the proper flow model to use and characterize design of the gas flow from dense to highly rarefied state, right? So that is this about Knudsen number, right? So let us just come to the moment where we were discussing about. So it is the microscopic detailing where the length scale is micron, and then microscopic, and in microscopic the order of centimeter or meter. So here what we were saying, this one centimeter to meter. Then scale of study is in this order, right? So what I'm saying is it is important. So in the macroscopic level, develop equations called macroscopic level balances where this concerned with the quantities or properties at the entry and the exit point only. So in this particular CSTR reactor, if you see, only entry point and the exit point you are bothering about, and you are not bothering about anything else, right? So concerned with the quantities or properties at the entry and the exit point of the system for the change occurred in the system, right? Does not consider details of what's happening inside the system. So that is the length scale that you are actually looking at is order of centimeter or meter, right? So that is the one thing about this particular thing. So I will be just coming to continuum hypothesis. So far we have already discussed about the continuum hypothesis. So let us just very briefly, so molecular picture you have discussed. So TP at microscopic level is considered herein where the continuum hypothesis is valid without any restriction. So transport phenomena is considered here, and thus the to recapitulate a few important basic concepts of temperature, these transport phenomena such as continuum hypothesis is there, transport mechanisms are there, and constitutive equations of transport by molecular mechanism you have studied. So what is continuum hypothesis? So we have discussed anyway if the Knudsen number is very small. Let us again discuss. Here the physical properties are assumed to be distributed throughout the space. The physical properties such as velocity, temperature, pressure, density, stress, electric field strength, etc. they are assumed to be distributed throughout the space, right? And then every point in the space has a finite value of such properties from one point to another. Like we were discussing in this CSTR reactor where I was saying that the distribution of the density, viscosity, and then this velocity, these things you have to actually look at. The properties, the fluid mechanical properties are same. They are not varying with the space within the system that you are considering under the consideration, right? So properties may change value, and there may be even the surface where properties jump discontinuously. So that those things will be handled, and we will be discussing them in the subsequent lectures. So it does not allow properties to become infinite or to be undefined at any single isolated point, right? So that is the one thing that has to be taken into the account, right? Let me just see if things are normal there. Yes, and so far we have discussed these things about Knudsen number, about continuum hypothesis we are discussing. So it does not allow properties to become infinite or to be undefined at any single isolated points, right? So that is the thing, that was the main agenda of this entire discussion till now. So I am moving slowly because I will be taking you to main concepts in the derivation that sir has had with you, and at the end, half an hour, we will be discussing with the questions that are there around this. Though these questions are just a kind of assumption based question that are not that deeper, but meanwhile, while discussing these, I will be penning down some questions to you, some terms. I will be explaining some physical concepts or the physical feel of the terms coming out in different expressions. That is more important, and you may have some direct questions directly coming out of those discussions that we are having. Maybe those discussions you have had left, you was not told in the classes, but they are there based on the experimental observation that we are having regularly during the experimentation that I am doing in my PhD curriculum, right? So, so precise continuum hypothesis states what? Reason in which physical properties to be described are subdivided into a set of infinitesimal finitesimal volume element, each of which simultaneously following. Each volume element should be small enough to so that properties are uniform. Any spatial variation in the properties inside the volume element are negligible. Each volume element should be large enough to contain a statistically large number of molecules so that the local thermodynamic equilibrium is maintained. So based on this, you may have questions. So each volume element should be large enough to contain a statistically large number of molecules, right? So that the local thermodynamic equilibrium is maintained. Why you want large number of molecules in a given volume element? And options will be based on that local thermodynamic equilibrium. So like if we can write some question, so why each volume element should be large enough, right, to contain a statistically large number of molecules, right? Large number of molecules. So option A is to ensure infinite number of collision among molecules. To ensure infinite number of collision between molecules. B option is ensuring infinite number of collision among molecules to establish what? To establish what? Local thermodynamic equilibrium is maintained both A and B. The option is none of these. So you just solve this and let me know what you are actually thinking about the question that you are solving, right? So if you see the question that is here is this one. So both A and B is correct. So both A and B are correct. So option C is correct. So you may just go through these questions at your will, and these questions will be definitely helping you in order to have some knowledge about the subject, right? So list, it's just direct question. Which example violates the continuum hypothesis? So any example that you know, it's the kind of revision that we are having right now. Any example that you are having, which example violates the continuum hypothesis? Which example violates the continuum hypothesis? The answer to is this is flow of gas in small pore. Flow of gas in small pore. So small pore, what it means? It's Newton diffuser. So suppose this is the small pore and through this gas is flowing. So here the kind of values that you will be calculating here, this is the diameter d. So this molecular size is comparable to this d, and that's why this is very large, and that becomes the favorable situation where this continuum hypothesis fails, right? So basic problems in continuum mechanics is to describe the response of the material to stress, right? That is the basic problem. So in the continuum mechanics, whatever you are doing is very important concept for entire transport phenomena is what this continuum mechanics, what it wants to do, it wants to what? It wants to describe the response of material to stress, right? The response of material, right, to stress, right? So if it wants to define the response of material to stress, so there is this a quantitative statement of that response. So whatever response it is describing at the response of material to stress, and whatever response it is describing for the material to stress, okay, is quantitative statement of that response is known as constitutive equation. So constitutive equation, what it is doing is very important concept. This is actually qualitative statement that is telling you mathematically how the material is responding to the stress, right? So a model which describes how material will respond to stress. Model describe how material, suppose this was the material that you are looking at, suppose it is rubber. So how this rubber, describe how rubber will respond to stress. right? Or any fluid that is applied stress, right? So transport mechanism, you know that if temperature and concentration is any material is perturbed so that they become non-uniform, then gradient tend to disappear over time. Same is true for the velocity variation within the fluid. Spontaneous dissipation of such gradient is fundamental and far-reaching observation. So energy concentration and material and the momentum of the fluid stream tend to move from the region of higher to the lower intensity. Okay, so that is one. So there is these important fluxes that comes into the picture for the flux, for the momentum, concentration, and the heat. Each have two contributes, right? So fluxes are those quantities, i.e., energy, concentration, and momentum. Each have two contributions. So any flux, whether it is energy, whether it is concentration, or the momentum. So let me just have the picture clear for this also. So if it's energy transport, momentum transport, and then concentration transport. So in each of these there are two types of fluxes. Okay, one is this convective transport, plus another is this molecular or diffusive transport. Convective transport, which is because of the velocity or the motion of the fluid element that is there, and another one is diffusive, which is happening because of the molecular collisions. Diffusive transport, which is happening because of the chemical potential gradient, right? So this convection part can be described in general manner. Molecular part of the transport process are specific to given material or class of the material, thus their constitutive equations are related. So molecular or the diffusive transport which originates from the intramolecular. So these originate from, we just have that, originates from where? Intramolecular forces, right? Intramolecular forces and relative motion, right? So that is V minus V average. So these things we have studied, right? Average molar average velocity, mass average velocity, those things in the diffuser, in the mass transfer, mass transfer, right? So so now you understand that molecular flux to material property. So it is a material property, and then this gradient of the temperature, concentration, and velocities are the important parameter that actually dictates the rate at which the transpose will be happening. So in the heat conduction, you had this very great equation for the flux, which is Q equals to K. Temperature in whichever direction it is reducing, there will be the flow of heat, right? So this is this equation. K is the thermal conductivity, right? Thermal conductivity. Okay. In a moving fluid, heat flux vector represent energy transport related to the mass over velocity, and because energy flux related to the fixed coordinate has convective contribution as well, right? So that is the one thing, and it is very important now to understand that in any fluid, whatever you are dictating, this K, which is the thermal conductivity, you are actually taking that as a uniform. So Q equals to minus K delta D. K has no preferred direction, whereas the flux has the same direction as that of the temperature gradient, right? So the material, which includes most solid and the almost all the fluids, obey this point are isotropic, and then material that are anisotropic, which are having an internal structures that makes thermal conductivity depend on the direction. For example, anisotropic materials, i.e. Q equals to minus K delta T, the scalar conductivity must be replaced by the conductivity tensor such that this Q is written as, in that case, this Q will be Q vector minus K. It is the thermal conductivity tensor, and this is the direction, right? So in materials which are anisotropic, for example, some rocks or some liquid crystals, liquid crystalline materials, they are having different properties in different direction, and in those cases, this becomes very important to know how they are behaving. So in such anisotropic materials, the direction of the heat flux and temperature gradient differs from each other. So it's not same, right? And similarly, we had this mass transfer equation derivation. So for mass transfer, the flux can be written as J equals to minus rho dAB, right? So mass CWA is this mass fraction of A in the binary mixture, okay, and this is equals to minus dAB. Okay. And rho is this density of the binary mixture, right? So two mixture A and B are diffusing to each other, and then C, right? So this rho into W, you wrote it as Ca, which is the concentration of the species A, right? So what does it mean? Whatever flux is happening because of the mass transfer, which is leading to the concentration gradient delta Ca, is, so flux is directly proportional to the concentration gradient with the proportionality constant which is coming up here is diffusivity, which is dA. Okay, so again these dAB can be anisotropic. So that is the thing that has to be taken into the account. Okay. So then you had this stress and momentum flux discussions. So what I am saying is, let me just take the slide now so that I can take you very rapidly to. So these were the discussions that you had stress, momentum, flux. So local rate of momentum transfer in the fluid are determined by the stresses, and these points has been considered as a normal and then this stress vector, and the component of this stress vector in different directions, stress vector for the two component normal SN and the tangential SN, which is S1 and S2 to the surface, has been considered and told you that S equals to n cap minus sigma this. So this tensor, this is stress tensor, is defined as this. You see here the line component are there, and the diagonal component, which are the normal stresses, are defined as this pressure plus deviatoric stress, right? And now here this sigma ij has been defined like this, and then theoretical delta function has been defined having 0 if I is not equal to j. So now, based on the analogy, you had this equation for the tau, and then this for the heat transfer, for the mass transfer, and for the momentum transfer, which is the Newton's law, right? So these three are coming into the picture, where this one, these are having the unit of diffusivity, which is this meter square per second. Here, for the case of heat transfer, you can convert that after dividing it with rho Cp, and then clubbing that into the alpha, which is K by rho Cp, and this is this thermal conductivity. Then there is this DAB, which is anyway same as that, and then this kinematic viscosity, which is coming at mu, which is dynamic viscosity divided by density, mu by rho. Okay, so that is the picture. So I am taking the slide so that we are fast, right? So their ratios provide comparison of intrinsic. So I will be having some questions, so that will be helping you in these terms, right? So let me just take these questions first, then So let me just take this. Okay, it is not happening. So let me just clean this one here. Okay. So what is the length scale in the case of transport phenomena at the molecular level? A macroscopic level, right? So macroscopic level, what was the length scale? You had this centimeter to meter, right? A is correct. And then in this one, what you remember? What is it in you had? Microscopic. So microscopic, what you had is micron to centimeter, right? B is correct. These questions we have already discussed, right? And that's why I had those discussions so that you can solve them very comfortably. What is the length scale in the case of transport phenomena at the molecular level? So molecular level, you remember the order of nanometers we were dealing with decimal micrometers. So C is correct. And about each we had the discussion here. I think this slide we were having. So there is no problem with that. I'll just put that here. Now, which of the following points are true with respect to the continuum hypothesis? So A is physical properties are assumed to be distributed throughout the space, right? Second is every point in the space has finite value of such property and does not allow property to become infinite or to undefined and undefined at any single aesthetic point. For from one point to next point, properties may change value and there may be even the surface where properties jump continuously, right? Discontinuously. So all of these are true. So if you remember our discussion very carefully, option D is correct answer, right? D is correct. So let's just so that is important, right? Whatever discussions we are having, these discussions will be helping you to solve, right, questions, right? So let me just see it is here. So yes, it's A. Let me just see. For first it is A. For second it is B. For third it is C. And for fourth it is D. Right. Now flux says of temperature, concentration, and momentum have following contributions. What is molecular transport and convection transport? Both molecular and convection transport are D. So which of the following is correct? Now only we have discussed that they are having both contributions, which is C is the correct answer. C is the correct answer, right? Now let us move to the next question. That is equation describing the time rate of change of density at a fixed point is known as time rate of change of density. You understand? Now that we have not discussed, but with the fluid mechanics concept, if you remember, we will be anyway discussing this, and then we will be coming to the point that is very important here, right? So now what I am saying is I will be putting some questions and we will be solving them. Now we will be mostly dealing with the dimensionless numbers that are actually dictating the amalgamation between these different transports of heat, momentum, and the mass, and how they are leading to the formation of a wonderful branch, wonderful subject which is transport phenomena, and in turn here the advanced level course which is transport phenomena of non-Newtonian fluids. So how they are actually helping you in building up the concepts for understanding weird fluids which are actually real fluids like time dependent fluid, time independent fluid, and then viscoelastic fluids, which are far away from the proper Newtonian fluid behavior, are being explained by the physical understanding of basic transport phenomena subject, right? So it's just like okay. So question is, rate of viscous momentum transfer related to heat transfer. Heat transfer through conduction is known as, options are Biot number, B is Schmidt number, C is Newton number, Nusselt number, and D is Prandtl number. So which of the following you think that is correct? So with this kind of question you may think of that you will be getting in your exams. So let me just see if things are working fine and we are online, right? So things are working fine, and the thing is, so let me just put it here. So it's just, yes. So Biot number, Schmidt number, and Nusselt number, and the Prandtl number. Which of the following you think is correct? So rate of viscous momentum transfer related to heat transfer conduction, right? So you see that here you are comparing the fluid dynamics with the heat transfer. So this ratio is known as what? So if you remember, this ratio is known as what we call, let me just fix it. This ratio is known as Prandtl number. So the Prandtl number is defined as nu by alpha. So you remember that nu is what? Nu by rho, and alpha is what? K upon rho Cp, right? K upon rho Cp or mu Cp, if you remember, mu Cp, right? And this, if you define, it will come out mu Cp by K. And this is Prandtl number, which actually regulates the fluid transport to momentum transfer to the thermal diffusibility. Okay, so option D is correct answer. D is correct. Similarly, we will be having another question. We just fix it here. Right. Viscous displacement related to what? Related to transfer, relative to species diffusion. C is diffusion. A is known as what? Just think. What does it is? What do you think about this? What is this, right? So rate of viscous momentum transfer related to species diffusion is known as what? Biot number, Schmidt number, Nusselt number, and then Prandtl number. So if you remember, the answer to this is what? Answer to this is Schmidt number, right? It is Schmidt number. So Schmidt number is defined as momentum now again to DAB. And if you remember, it is mu by rho divided by DAB. So mu upon rho DAB, right? So B is correct. So now the another one is left out. Just think about that. Is what is when you are actually looking at ratio of diffusivity that arises in analysis of simultaneous heat and mass transfer. Ratio of diffusivities that arises in case of heat transfer and mass transfer, right? So the options are place number, Prandtl number, Schmidt number, Biot number. Okay. So answer to this is, it is clear to you. Let me just fix it here. Is this Lewis number equals to what? Diffusivity, heat transfer, which is alpha, divided by partial density, right? So you can write it K upon OCP. And if you rearrange it, you will be getting Lewis number equals to Schmidt number. So interrelated means if the Prandtl number is low, then Lewis number will be high, right? And so forth. So these were the discussion about the first lecture. Let us come to the point where we will be discussing about the second lecture, that was around this mass conservation of the momentum conservation. So now onward we will be very fast in terms of discussing the concepts. So all the things were same. So let us just put it here so that we gain some knowledge. So I will be just putting it here so that it becomes easy for me to explain everything. So okay, so this was the second lecture of the week. So first you have to fix the control volume, right? You just see if somebody is here. Stay in the cardboard problem. So yes. So let us just see this. Yes. So equation of continuity we are going to derive, which is this control volume, which is delta x, delta z, and delta y, delta z, delta x, delta y, delta z volume. This through this whatever mass is entering, that is leaving. So or whatever is being accumulated. So that is, we are solving the mass conservation equation. So rate of mass accumulation equals to rate of mass in minus rate of mass out, and that derivation if you do, finally you will be getting the main expression, which is this one, where you are actually having this del rho by del t minus del dot rho v, right? So in the Cartesian coordinate only for the time being we will be discussing, and then we will be going for the any other coordinate system, right? So if you see, let us just change the color. Yes. So now till now what you had is this this del rho by del t equals to minus del r dot rho v vector, right? So rate of increase slash accumulation of the mass per unit volume equals to net rate of mass addition 1 meter volume by convection, right? And then continuity equation describes the rate of change of fluid density at a fixed point, right? So it is very important. So rate of change of fluid density at a fixed point, right? So that is the one thing that was important. And if you see this question, equation describing the time rate of change of density at a fixed point is known as what? Continuity equation. So you are having option C is correct. Answer C is correct answer based on the discussions that we had, right? Now let us come to the next. For an incompressible fluid, the equation of continuity can be described as, so if a fluid is incompressible, okay, so if the density is not changing with time, which is the fluid which is incompressible, then this term that was there, if we just select it here and put it here, and this term becomes what? This term becomes 0, and then what you will be getting, 0 equals to minus of del dot v. Okay. When your density is constant, this rho comes out, and that you will be getting equals to 0. For a constant density fluid, constant density incompressible fluid, incompressible fluid, what you are getting, this del dot v equals to 0, and that's what you have to see. This divergence of temperature is 0, momentum is divergence of velocity is 0, right? D is correct answer, right? So that's what we were discussing. Let us just put it here. Let's put it here, this one. So if in this equation, continuity equation describe time rate of change of fluid density at a fixed point, right? And then del dot rho v is nothing but the divergence of mass flux, right? This is mass flux, and here rho, if it is constant, it comes out of the delta, and then this del rho by del t will be not changing because you are dealing with the incompressible fluid, so this will become 0, and finally you are getting this del dot v equals to 0, which is for the constant density fluid which is incompressible fluid, right? So now if you see that for rectangular coordinate you had this one, it is the expand, these three terms are expansion of del dot rho v, okay, and this is del rho by del t, right? Anyway, so this is for the cylindrical and this is for the spherical. So these equations you don't need to memorize, rather these will be finding in standard books like BSL and RP chapter, right? So these things you can refer based on your requirement during the solution of your system or analysis of your system, right? So let's see equation of motion. So now the equation of motion derivation is done. So this is the derivation for the Navier-Stokes equation. Very easily sir has defined each and every term and took you to the Cauchy's equation of motion, and that is where which is valid for both Newtonian and non-Newtonian. Afterwards, in the Cauchy's equation, you are having some assumption that is specifically fixing it for the Newtonian fluids that you were doing so far in basic transport phenomena courses and in fluid mechanics courses. But here you are using these Cauchy's equation where you are keeping the shear stress term which is sigma as it is, and then you are putting your non-Newtonian models of fluid or the analysis of non based on the instrumentation, whatever you are having, shear stress to strain data, based on that you are doing your analysis, right? So here, like you had this convective and molecular transport, both you have considered. So here the main thing is rate of increase of the momentum of this control volume is equals to rate of momentum in minus rate of momentum out plus whatever external forces of the fluid is leading to any contribution to the momentum inside the given control volume, right? So these each terms you have defined for x component of momentum entering to x component, component momentum entering, whatever it is leaving. So and then for different phases you have, and then you have added all the phases together to reach to the point where you are having the main expression, that is this one. For x direction, whatever change is in the x direction is there, x direction contribution, momentum addition from x direction, y direction and z direction, and then this body force whatever is there. Here you are considering the gravity body force to be there. Okay, so the final expression that you are having is this one. So here the combination combined mass momentum flux tensor, which is phi, is convective mass flux, which is rho v plus molecular mass flux, which is pi. So you can write it as pi equals to, and now this molecular mass flux is what? P plus deviatoric tensor, right? So this P plus deviatoric tensor plus rho Vv, it will give you, the rho Vv is what? It is convective momentum flux tensor, right? And this will be giving you, so detailed analysis. So this is the Cauchy's momentum equation, which is very general equation. So far you are not having any assumption about the Newtonian or non-Newtonian. It is simple, the balance of momentum transfer across this control volume. So here the rate of increase of very important equation, I will be just expanding it up because this is the one that will be actually, let me just, if I can, okay, so this rate of increase of momentum per unit volume with time, it is rate, is equals to rate of momentum addition by convection per unit volume. Then rate of this is the by convection, and this is by, this two term is by rate of momentum addition by molecular transport per unit volume, and then this is based on external force per unit or force on the fluid per unit volume, right? So this is Cauchy's momentum equation, and this is, and it's the same Cauchy's momentum equation. If you write in the Cartesian form for the x, z, and x, y, and z coordinate, you will be having this, and based on that, the different component, which is tau x, tau y, tau z, tau x, y, tau y, z, tau zx, and this tau x is equal to tau y z, and tau y z equals to tau z y. These things will be actually related with each other. Similarly, in the standard textbook, you can find the momentum equation. So the basic steps will be same for the derivation. So this you can use the momentum equation in the cylindrical and the spherical coordinate, and you can refer the standard textbook for that. You don't need to revise. If there is a question in the exams or in the tests, you will be actually provided with these equations and basic assumptions. You need to remember what assumptions that you are having in the case of asymmetric problem, and then there is some assumptions related to which you are having duplication approximation by it, or you are actually neglecting the inertial influences, only considering the diffusive influences of the viscous dissipation part. Those things you need to consider in your considerations, right? So these are values you will be getting in the standard textbooks. So that is what I wanted to tell you about this particular, let me just fix it here, this particular lecture, right? So let me just fix it here. Yes. So this was this equation, right? So here you had this partial time derivative, then total time derivative, which is leading to substantial time derivative. Those definition you have had derivation, and substantial time derivative is nothing but the right hand side, left hand side of the continuity equation. Also, if this C is replaced by rho, then that you can write as d, capital D rho by dt, right? So that thing is there. So till now what we have derived is, let me just see. main expressions, that is the, let me just put it here. Yes. So the main expressions that is here, we will be actually looking at those. So let me just, yes. So so this so far what you have given for equation of change for isothermal system, equation of change for isothermal system, right? What it is in terms of substantial derivative, in terms of substantial derivative. You remember that substantial derivative, right? Whatever we were saying, uh, the substantial derivative is defined as what? Let me just write it again because it will help you. Any property, it is there. Suppose d by dt. This is equals to del by del t, right? Plus v vector into del. Here that property will be coming out. So this is the substantial derivative, this capital D, right? And if this substantial derivative in this form, if you write continuity equation, then you are getting d rho by dt equals to minus rho del dot v vector, right? And then momentum equation, rho dv by dt equals to minus delta minus del dot tau plus rho. So now for constant density and viscosity for Newtonian fluids, this tau, you may write as what? Tau equals to what? Del v vector plus del v vector transpose plus this is 2 by 3 mu minus a, measure of the molecular diatomic characteristics. And here, what you are writing here is del dot v vector and chronometer. So equation of motion under these conditions will reduce to, equation of motion under these conditions will be equal to rho dv vector by dt equals to minus delta p plus mu delta 2v vector, right? Here this p is here, p is what? Small p plus the 2g, so it is actually containing the body force. So that's why it is written as capital, right? So this is the Navier-Stokes equation. So this is this Navier-Stokes. So now you are clear with these things. So there are different asymptotes about which we will be solving some question, but let me just say it. Which of the following time derivative is most reliable for if there exists flow in the system? So which of the following is most reliable, right? If you remember, we had already discussed for the flow in the system, okay, which of the the system is most reliable, right? So let us just see solution to that. So substantial time derivative is the most reliable because it is actually giving you both, and there are spatial change, right? So B is correct answer. So you can look at this second lecture of the week. I think slide number somewhere 17. 16 or 17, you will be actually 18, I think. You will be actually getting basic concepts about the same, right? So which of the following equation holds well if there exists very slow motion or negligible convection, right? So option A is Euler's equation, option B is Stokes flow or creeping flow equation, option C is both Stokes flow and the Euler's equation, and option D is none of the above, right? None of the above, right? So let me just see. Things are all right. So, so that is one thing. Yes. So which of the following equation holds well if there exists very slow motion or negligible convection, right? So you just look at this. We just have this 2 hour session. We are actually revisiting the concepts that was there, and around these concepts we are generating questions as well as the brushing up the basic concepts or the physical understanding of the terms that are there, and how much it is important for you to actually uh, thoroughly understand the entire subject, where you are simultaneously learning the aspects of heat and mass and momentum transfer together to non-Newtonian fluids which are under consideration. Okay, so if you see this, so what I am saying is, let me just expand it a bit. Yes, so what I'm saying is this, before solving this we had these equations, right? What we were solving, this one, right? Let us just take it here. So here if you see, when acceleration term is neglected in the Navier flow, so if you neglect acceleration, right? Let me take it color. Neglect acceleration term, right? If you neglect acceleration term, then this will become 0, right? 0 equals to minus delta p plus mu del to v vector plus rho g, right? Hello. So what is more important is, if you see this Stokes flow, let wait. आधा घंटा बस बचा है। हाँ ठीक है, भयंकर आपको बताते हैं आइडिया oh sorry, someone mocked me. So anyway, this this 0 equals to minus delta p plus mu del 2 v vector plus rho g, right? So this thing if you see, the acceleration is removed here, so this comes into the criteria of this Stokes flow or creeping flow equation, right? This equation is quoted in the lubrication of theory, where this study of particle motion in suspension flow through porous media etc, right? So there it is important, right? So now when these viscous forces are neglected, then rho dv vector by dt equals to minus delta p plus rho g. So if you neglect this term, we just take different color for this. If you neglect this term, right, this term, viscous term, then what you are going to get is rho dv vector by dt equals to minus delta p plus rho g, right? So this is called as Euler's equation for inviscid flow. Okay, Euler's equation for inviscid flow means viscosity 0, or there is no viscous dissipation in the flow situation, right? So there are no true inviscid fluid. It is just hypothetical case, but there are many flow in which viscous forces are relatively unimportant, right? And if the viscous forces are relatively unimportant, then what you are having this Reynolds number equals to inertial force to the viscous force. And it is in, the Reynolds number is very high, right? That flow around airplane wings, flow of river around upstream surface of bridge, right? Some problems in upstream surfaces of bridge, right? Some problems in compressible gas dynamics, and the flow of ocean currents. So these are some examples of that. So based on that, if you see the question that was there for us to solve is, which of the following equation holds well if there exists very slow motion of motion or negligible convection, right? So then Euler equation is holding, or then this Stokes flow or creeping flow is important, and then Stokes and Euler both are important, and none of the above is. What I'm thinking is this Stokes flow or creeping flow is the answer to this given question, right? And if you see this, let me just fix it so that I can see both the screens. It is here. Let me just put it here. Yes. So if you see this particular, based on this discussions that we had here, neglecting as Stokes and creeping flow, we can say that this is option B is correct answer. Okay, option B is correct answer, right? So that is it for this second lecture of the week. And now the remaining 25 minutes, what we will be discussing is, we will be discussing the third lecture, which was around non-isothermal thing. So before that, let me just see this 10, 11, 12, 13 and 14. So these questions we will be discussing about the third lecture. Okay, and I hope you will be gaining concepts. So before that, let me just take the slide over here so that we can discuss it very quickly, because the content in the third lecture was a bit more, and the time that we are having is very less now. So it is like very tight to complete all the 3 lectures about transport phenomena. Rather, it is of the non-Newtonian fluids within the framework of this half an hour. So like non-Newtonian fluids, within 2 hours of the session, you are actually binding it completely, right? So let's just third lecture, let me just put it here. So like very less time you are having, and the content is very high. So that's why we use both slides as well as step-by-step writing process so as to make it easy for you to understand each terms and what the physical meaning of those terms are, right? So now this is the third lecture of the course Transport Phenomena of Non-Newtonian Fluids for the 4th week. Here till now we had this this is a recapitulation slide where you had got the enough knowledge about the continuum hypothesis, transport mechanism, molecular transport mechanism. Then you had this partial, total and substantial time derivative definitions, and then you had this continuity equation, momentum equation derived, right? and then Cauchy's equation of motion you have derived, right? So equation of change for non-isothermal system that we are going to discuss. What I will be doing is I will be discussing with you this particular slide, right? Let me just hide it. So this particular 26 slide, I will be taking you step by step, slide by slide, and then at the end we will be solving those 5 questions that is remaining from question number 10 to question number 14 in our basket, right? So energy equation, which is the conservation of energy. So here, if you see that you are actually considering a stationary volume element. So like elements that you have considered in each of the setup. So suppose this kind of element you have considered, and from here you had this. Say suppose for the case of conductivity equation balance, you had this mass flow in minus mass flow out equals to whatever mass is being accumulated in this particular control volume, right? And now, if for the momentum you have derived it, so for the momentum, whatever momentum is being accumulated in this particular control volume is nothing but whatever momentum is getting in through different x, y, and z direction, and then whatever it is leaving, right? And then whatever momentum is being transferred based on what? Based on the term which is coming because of the body force, right? So that was the main thing about the balance that you are having. The basic definition for the balance of momentum or the mass is same, but it's just how you are handling the terms and how you are handling the fluid dynamic or this transport phenomena parameters in order to have a quantitative mathematical form that will be dictating the entire flow through your system, right? So you came to know that there are fluxes, and each fluxes are having 2 contributions, which is one is because of the convection and another because of the diffusion. And in these terms, if you see in each of these terms, whether it is momentum equation or the thermal balance equation, or in the future if you see this mass balance equation, you will be getting these 3 terms that is there. These terms will be actually having contribution from both convection and molecular transport, right? So that was the main thing about which we were discussing right from the beginning in this particular lecture today, and in the entire week sir has lectured you around that, right? So this, considering a stationary volume element fixed in the space through which the fluid is flowing, right? That is important thing. Then now the kinetic energy and the internal energy may be entering and leaving the system by convective transport. So whatever kinetic energy is entering to the system or leaving to the system may be having some flow associated with it. That is nothing but the convective transport, which is discussed here, right? So energy may enter and leave system by heat of conduction. So that is another point that is there. And then work may be done on the moving fluid by stresses, which is also molecular process. So work done by stresses are the molecular process, right? So you don't have to get confused based on this molecular level discussion that we had today, because there that is different thing. But here also the origin of stresses which are being applied in that control volume, putting a kind of work on the fluid element, and that arises from this molecular process, right? This include work done by pressure and the viscous forces, right? So work may also be done on the system by virtue of external forces such as gravity, such as magnetic field, such as electric field, such as these surface forces which are there. Sometimes these intramolecular forces also come into the picture in these setups, right? So what I'm saying is, if you look at the thing, the entire this particular slide dictates you the entire picture of what the conservation of energy means, and how this conservation of energy is actually controlling most of the processes, right? If it comes to the thermal balance part, right? So rate of increase of kinetic and the internal energy, so combined kinetic and internal energy you are looking at, is equals to net rate of kinetic and internal energy addition by convection plus net rate of heat addition by molecular transport, which is conduction. Here the conduction is taken as the molecular transport, and which is happening because of the stresses, right? And then rate of work done on the system by the molecular mechanism such as stresses. So that is another thing, and this is because of K into gradient of T, divergence of T, if you see. So del T, right? And then rate of work done on the system by external forces such as gravity, electric field, magnetic field, or the surface forces, right? So if you see this, the kinetic energy in the system is the energy associated with the observable motion of the liquid. So you can observe the velocity, you can measure the temperature, you can measure the pressure, you can measure the viscosity, you can measure the density, you can measure the fluid property or the some properties related to the flow, which is actually responsible for the flow or the result of various forces which are being imparted to the fluid because of the stresses that are felt by that fluid. Okay, so what I'm saying is this particular kinetic energy is the energy associated with the observable motion of the fluid. So this velocity you can observe if the motion is happening, right? So this can be termed as 1 by 2 rho v square equals to 1 by 2 rho v dot v in the vector notation, right? So the internal energy is the kinetic energy of constituent molecule calculated. So internal energy is also the kinetic energy, but it is sum of all the constituent molecules if you calculate together in the frame moving with the velocity of the system. So plus the energy associated with vibrational and the rotational motion and molecular interaction of all the molecules. That is important here. So potential energy do not appear in this equation, as preferred to consider the work done on the system by gravity. So the potential energy is taken care by the body force, right? So you had to actually, and in the subsequent slides, sir has also explained that how this gravity can be converted as if it is a part of the potential energy, and it has been added back to the left hand side, where the kinetic energy, internal energy, and the potential energy together had balanced themselves with various contribution of energy through pressure forces, through viscous dissipation or the stresses, or viscous heating, so to say, or the gravity, or the body forces. What I'm saying, okay? So viscous heating source term is not appearing separately here, already included in the rate of work done on system by molecular mechanism, by stresses. So by the stresses, whatever work is being done, that is nothing but that is del dot tau. I think that term comes up into the picture, and that is actually taking care of the molecular mechanism leading to the viscous heating source term. Okay, so chemical, electrical, and nuclear source terms can be included in the right hand side in overall conservation of the energy of specific considered problem, right? So this you see, let define energy vector E, which include first three terms in right hand side of the equation 1. What is equation 1? The equation 1 that we had is this one. First three terms in the right hand side, right? So these things, if you see, first three term in the right hand side. So this term, this is kinetic energy and internal energy addition by convection, and then rate of heat addition by the molecular transport, which is conduction, and then the rate of work done on the system by the molecular mechanism, which is stresses, right? So let me just see, if you add these terms here, convection, molecular transfer, so all the term except work done due to external forces such as gravity and reaction etc are not included. And if you see that, and then this del dot v vector part, you can re-expand that there, and these expressions you can get from any standard books, right? So this, if you see this, we have already known that the total molecular stress pi can be split into two parts, which is one is pressure forces and then gravitational stresses, right? And then if you do so, and then you reclub those things, you will be finally getting the terms like this. So these terms you will be getting. So this is the final E bar that you was calculating here. This tau b is this heating, viscous heating part, Q is coming up, and then this is another, right? So if you see this, so here internal energy per unit volume is U bar, U is internal energy per unit mass, and then based on that you have this kinetic energy per unit volume, and all those things add up together, and based on that you had this control volume and then balances like we had in different terms. So you had this final expression, right? And this final expression says that the increase rate of increase of the energy per unit volume, this internal energy plus the kinetic energy equals to rate of addition of the energy per unit volume by convection plus the rate of addition of the energy per unit volume by conduction, and then the rate of this is K into delta T, and then rate of addition rate of work done on the fluid per unit volume by the pressure forces, and then this is rate of work done on the fluid per unit volume by the viscous stresses, right? Viscous stresses are important term which is leading to the viscous heating, right? And then this is V dot G. About this you had how this V dot G is coming up into the picture, and then leading to the some so rate of work done on the fluid per unit volume by external forces. So these things, so if you solve this V dot G and you write this G as this, then you can write it in terms of potential, and then finally whatever expression that you are having is this one, right? So this is the special form of the energy equation that you had, where this is the final energy equation form, where you are having kinetic energy, internal energy, and because of the convection, because of the conduction, and then pressure forces, and then this stresses, viscous stresses, and then this body forces, right? All the terms are leading to the energy transfer, right? And how it is being added to the balance we have seen. So if you see some special cases sir has derived, so if you follow this, we can have equation of change. So equation of change for combined all the energies was this one, but equation of change if you write for only kinetic energy as follows. So what you have to do, you have to do the dot product of the velocity vector with equation of motion that you have derived in the last lecture, right? And then this is for this internal energy balance, kinetic energy balance you had, and then the equation of change for the internal energy balance, and then there is equation of change for the enthalpy balance, and then there is equation of change in terms of measurable quantity, which is temperature, right? So in terms of measurable quantity also you have derived your equation of motion, right? So what I'm saying is this one, that some questions we will be solving, but before that what we will be doing is we will be just looking at what have been taught till now, right? So let me just see. Internal energy of the system is associated with kinetic energy associated with the molecule, energy associated with the vibration and rotation of the molecule, energy associated with the molecular interaction of the molecule, all of the above A, B, C. So what I'm thinking is we have just discussed about the same. Option D is correct answer. D is correct answer, right? So that is one thing. Another one is degradation of the mechanical energy into thermal energy is known as viscous dissipation, convection of energy, conduction of energy, and then D is none of the above, A, B, C. Okay. So if you see, so for the above question we have seen the all of the above is correct, but for this question, if you see the viscous dissipation term that was there, about which we will be discussing now. So this is this viscous dissipation term. Let's just see. Okay. So A is correct. If you want me to explain you a bit about this, then we need to just discuss it in terms of what has been discussed in the class. Like this viscous dissipation term is very important, and this is what you had this tau, somewhere you had this minus of tau double dot del V vector, right? So you know that this is this gradients of velocities, and this is this tau part which is coming up into the picture. And above this you had the large expression. It is degradation of mechanical energy into the thermal energy. Okay, so degradation of mechanical energy it's slide 20 in the third slide of the week 4. Degradation of mechanical energy into thermal energy. So it generates heat, right? And it is known as viscous dissipation, right? It is known as viscous dissipation. So this can produce temperature rise in the system with large viscosity and velocity gradient. So what it does, let me just put it like this. Okay, so let me just put it like this. Let me just save it because sometimes it actually fails to do so, and it's already 32 slides. So, and these slides, PDF of this, I will be sharing to you on the Google Drive. I will be dictating you. Meanwhile, I will be dictating you those things. Okay, so if you see what it can produce, this can produce temperature rise. So temperature rise can happen. Okay, and this temperature rise can lead to rise in system temperature, and this leads to large viscosity gradient because viscosity is depending on temperature, and velocity gradient. As you know that once the viscosity is thin dot thickened, there is this viscous dissipation or viscous diffusion forces reduces a bit, and then there is subsequent flow structures coming in the picture. So this lubrication, rapid extrusion, and high speed flights, they are having some of the example of this, right? So now this question is done. Let's solve the next question. If there exists nuclear energy in a non-isothermal system, associated term in the equation of energy should added as viscous dissipation term, source term, work done due to pressure term, none of the above A, B, C, right? So it should be added as a source term, right? So as we discussed, it is like gravity, electric field, magnetic field, surface forces, reaction term, viscous term, those things will be added in the source term. So B is added, right? So it's slide 6 of the lecture, right? Now next question is, most of the equivalent form of energy equation is in terms of temperature, internal energy, enthalpy, none of the above, A, B, C. Most of the convenient form of energy is in terms of temperature, internal energy, enthalpy. So what we have discussed till now is it should be measurable quantity, right? It should be measurable. So whatever quantity in which you are in which form you are writing the governing equation, it should be measurable so that you can validate your equations with the experiments that you are doing, right? So let's just add it a bit. So its temperature, A is correct answer, because temperature is measurable, because internal energy, enthalpy, these things depends on temperature and they are not direct measured. So slide number 19, lecture number 13, you can refer this. And the last question is what? Viscous dissipation, right? Let me just fix it like this. So it's here, yes. So viscous dissipation in non-isothermal flow system is important when small viscosity and the low velocity gradient exist, high viscosity but low velocity gradient exist, high viscosity and large velocity gradient exist, small velocity but large velocity gradient exist. So we have just discussed in the last slide. Let me just put that slide here. So this one was the concepts that we have discussed. So let me just put it here. Yes, so it's large high viscosity and large velocity gradient. So C is the correct answer. C is correct answer. So what you came to know so far is these things. So if you remember, whatever thermal equation that have been derived till now is based on whatever understanding you had about the systems knowledge, right? But the main thing is these thermal equations, whether it is in terms of the equation of change for this kinetic energy, equation of change for internal energy, equation of change for enthalpy, and equation of change for temperature, or combining all these three, four together to tell you kinetic energy, internal energy, and this potential energy together to have this internal energy change, right? So what I am saying is these equations we have derived, right? So the equations that we have derived is this. Let me just have green color now. It is rho Cp dt by d time. It is the substantial derivative that you are having equals to k del 2t. These all are in Cartesian coordinate, right? Minus del ln rho by ln t. This is the value that we had derived it -1 for ideal gases. So that's why for ideal gases these equations reduce to something. Okay. Okay. So now if you see this equation. So one question I want you to solve is which of the following is not for ideal gases. Option A is the same option that just I have put. We just see it. Option B is what? Option B is what? Rho Cp cap. This is per unit mass. d3 by d time equals to k into t plus d e by d time. So this is the equations I am looking at and then giving you. And then BC is what? Rho Cv in terms of Cp and Cp. Cp minus Cv equals to R we have used, and then these conversions has been done. Equals to K into D minus P into D. Okay. And D that is there is rho Cp del T by del time equals to K del T, which is correct. So if you look at this carefully, then you will be getting that only these two are correct for the gases. This is for both. So when you do the PV equals to 1 RT, you use then you will be getting that del ln rho by del t, del ln t to -1 at constant pressure, and this will give you this one. And when you use Cv minus Cp, Cp minus Cv equals to R. Okay, so then you will have this one. So only if this is correct. This is for this stationary solid. Stationary solid. Okay, and there is two more equations that you can remember for now. Is for a fluid flowing with a constant pressure. When the constant pressure is there, so if you remember, for the constant pressure, this term goes to 0, and you are having this just these two terms, right? So that is there. So this term will be good for fluid flowing with constant pressure, for fluid with constant pressure. What you are having this dp by dt equals to 0, and then this will be going to 0, right? And then only this term you are having. And then similarly for this fluid with constant density also you are having this term 0, right? For constant density also, if we write fluid with constant density, what you are having this del ln rho by del ln t p equals to 0. So this will come again, you are having the same equation, right? So that is important thing for. So in this today's lecture we have discussed about all the concepts related to this basic governing equation, be it conservation of mass, which leads to the continuity equation, conservation of momentum, which leads to the Cauchy's equation of motion, or later the Navier-Stokes equation, and then how this can be used for the non-Newtonian fluids, and then the equation of change for energy. So all the equation of change we have discussed, whether it is energy, and in energy we have discussed about this very the specific equation of change for kinetic energy, enthalpy, internal energy, and then this equation of change for temperature, and then the combined of all things together we have derived, and we have seen some 20 to 21 questions around that. I hope this particular lecture helped you in some sense and cleared your concepts, so you can revisit these lectures at your will. So what I'm saying is, this is the course, right? Let me just get it here. If you see, these are the things. So this is the 4th week is there, so we have solved this. Now 5th week lectures will be coming up into the picture, and here you will be getting the problem solving sessions that we are having here. So all these are recorded and you will be getting benefited out of this, right? So thank you so much for your kind attention, and we will be meeting in the next week, right? In the next week we will be discussing some more fascinating concepts related to transport fluid for non-Newtonian fluids. Thank you so much.